Okay, let's get started with today's lecture. Remember last time we started talking about context-free grammars. Or CFG for short. We have given so far some examples, some example context-free grammars and the languages that they generate. Let's continue with some more examples. Let's first consider the following example. Given the following language L, W in 0, 1 star, such that W has twice as many zeros as ones. So basically in W, the number of zeros should be twice the number of ones. Let's just give some example strings. So for instance, W equals 0, 1, 0, 0, 1, 0, let's make 1, and then we need 2 more zeros. So in this string W, we have 6 zeros and 3 ones. Since the number of zeros is twice the number of ones, then it's easy to see that this string W belongs to the language L. Okay. Now, can we design a context-free grammar G for this given language L? As usual, let's start with our starting variable S. Remember, we were heavily trying to make use of principles of induction while designing our grammar. First of all, we need to provide rules corresponding to the basis of our induction. So while doing this, we need to consider which string could be the shortest possible string in this language L. Okay, so if you think about it, epsilon, the empty string, is the shortest string possible inside this language L, because in the empty string there are 0 zeros and 0 ones, and the number of zeros in epsilon then is twice the number of ones, because both of them are 0. This is our base case, just the empty string. Now for the rest, we need to think of applying the inductive component to be able to generate such strings in L. For this part, assuming that with this variable S we are able to generate shorter strings that belong to this language L, how can we extend them? How can we generate longer strings? To do this, let's write down a possible string that is not trivial, that is not epsilon, that belongs to this language L. So the next length of the string that could belong to this language, so epsilon has length 0. If we write down the next shortest length possible for a string to have is going to be 3, because we can have 2 zeros and a 1. Okay, so epsilon is one string. Another string that belongs to the language is 0, 0, 1, having 2 zeros and a single 1. But these 2 zeros and the 1, we may have different permutations of this. Okay, so we can have 0, 1, 0, or finally 1, 0, 0. Now, how can we extend such a string to define a general string in language L? Just as we did with the previous example, we can add S anywhere possible. So this basically corresponds to a longer string, assuming that S is capable of generating any string less than certain length k, then this whole string will be able to generate a string W with length k that belongs to L. We can do this for the other possible permutations as well. Insert S anywhere else, anywhere possible. Okay. Now, such a grammar will be able to generate all possible strings that belong to this language L. Let's consider yet another example. L consists of A's, B's, and C's, A to the I, B to the J, C to the K, such that I is not equal to J or J is not equal to K. To be able to design a grammar for this language, let's split the language into two. Let's say that L1 corresponds to the language where we don't care about the number of C's. Basically, we don't care about this part, but we only care about this part, that number of A's in here is not equal to the number of B's. So A to the I, B to the J, B to the J, C star, such that I is not equal to J. This is L1. We can similarly define a language L2. This time we don't care about this condition. So A star, any number of A's, followed by I B's and J many C's, or let's write it J and K as we have in the definition. J many B's and K many C's, such that J is not equal to K. It's easy to see that if I take the union of L1 and L2, it should provide the language L. Okay. Now we can actually even further split each of these languages. So L is split into these two languages. L1, we can split it into two languages as well. Let's say L11 is the part of L1, the strings in L1, such that number of A's is greater than number of B's. And the second language will be just the opposite. So A to the I, B to the J, and C star, such that I greater than J. And the second language, L12, is A to the I, B to the J, C star, such that I is less than J. Now again, if I take the union of these two languages, L11 and L12, I can get L1. I can define again two languages similarly to define L2 as well. Okay, basically I could define L21 to correspond to the set of strings where we have A star, B to the J, C to the K, such that J is greater than K, and L22 such that it consists of strings A star, B to the J, C to the K, such that J is less than K. Okay, similar to these ones. Now you should be able to see that if I take the union of all these four languages, it should provide language L. Which means that if I just concentrate on, for instance, creating the grammar that generates this language and creating a grammar that generates this one, and this one, then I can easily create a grammar that generates language L. Let's first start with the first one. How can I generate a grammar for this language? In other words, we want to generate the grammar for A to the I, B to the J, and C star such that I is greater than J. Again, let's think of in terms of induction. We will first create a starting variable S11, which will be the starting variable of the grammar corresponding to L11. Now for the base case, what could be the shortest string? Let's first forget about the C star part. Let's first concentrate on generating strings of the form A to the I, B to the J, such that I is greater than J. If we first concentrate on this part, our base case will simply be the string A, because in this string we have one A and 0 B's, so I is greater than J for this string. So this is our base case. To be able to apply the inductive component of our inductive design, assuming that S11 is already capable of generating strings of this form, how can we extend it of this form, A to the I, B to the J, such that I is greater than J? One way to generate such strings is to add yet another A. Okay, so remember that. So for instance, if I want to concentrate on A to the I, B to the J such that I is greater than J, I will have a string W that starts with A and the rest of the string is W prime. What are the possible cases for W prime? W prime may belong to, may have let's say equal number of A's and B's. W prime might be equal to A to the n, B to the n, because we are already adding an A at the beginning. So if W prime is in the format A to the n, B to the n, then W will belong to the language. A second case is that W prime is so that A to the I, B to the J, I is greater than J. Okay, so there are these two possibilities for generating a general string W. If W is already not equal to string A, W will start with the symbol A and will be followed by some W prime. And two cases possible for W prime. W prime may have equal number of A's and B's, or number of A's can be greater than number of B's. Now the rule, the inductive rule we have written down in here corresponds to this case. It covers all W prime or the generations of W following this case. W is a W prime such that in W prime we have more A's than B's. But we should also write down a rule that corresponds to this case as well. Okay? So basically W starts with A, and in W prime we have A to the n, B to the n. In other words, number of A's at the beginning is the same as the number of B's that follows. To be able to generate such strings, we will write down a variable E, and with the variable E, the rule for the variable E will be as follows. E, so in E we want to be able to generate strings of this format, A to the n, B to the n. To be able to do this, again we can use induction. The shortest possible string will be epsilon. Given a string already existing in E, how can we extend it for the inductive components? We can add an A at the beginning and a B at the end. So the simple grammar will be able to generate, with the variable E, we will be able to generate all strings of this format, A to the n, B to the n. So with these three rules, now we are able to generate all strings of the form A to the I, B to the J, such that I is greater than J. All we need to do finally is to be able to insert the C star at the end of all such strings. To do this, we simply write yet another rule that says you can take any string generated by this S11 and simply add a C at the end. Right? Note that with the following rule, using this rule for instance, I can start with S11, do a derivation extended with using this rule, S11C, again replace this S11C with yet another instance of this, S11, S11C goes to yet another S11C and C, so this corresponds to this S11, and so on. So by this way, with this rule, I will be able to have as many C's at the end of A to the I, B to the J as I want. Okay, so all these four rules together gives rise to my grammar that generates all strings in this language L11. Now similarly we can create a grammar for L12, which was a to the I, b to the j, c star, such that I is less than j. To be able to do this, let's write down the starting variable corresponding to the grammar of this language L12. The simplest case, let's first again concentrate on the a to the I, b to the j part. The shortest possible string with I less than j will be just b itself, okay, because we have more b's than a's in this simple string. To be able to write down the rest of the rules that will generate the strings based on induction, assuming that S12 is already capable of generating shorter strings belonging to this, I can just add yet another b at the end of such a string and get a longer string that belongs to L12. But similar to the discussion in here, this is not the only way to have such a string. It could be the case that the string ends with b, but we have in here a string with equal number of a's and b's. So to do that, to be able to generate such strings as well, we just write a rule that says S12 can also corresponds to E followed by B, where E corresponds to generates all strings with A to the N, B to the N. Number of A's some number of A's followed by the same number of B's. And if we add yet another B at the end, then we will get yet another type of string that belongs to this language L12. And finally, to be able to add C star, just the same as we did in here, we can just say take S12 and add SC itself. Again, following, if we are to repeatedly extend our S12 with this rule, S12C, then we will be able to add as many C's as we want at the end of our string. Okay, so S12 will generate all strings in L12, S11 will generate all strings in L11. Remember that we had created languages L21 as well, such that A to the I, well, A star, B to the I, C to the J, such that I is greater than J. I will not write down the grammar corresponding to this one, but you can, as an exercise, write down the grammar for this. Finally, we define the language L22, A star, B to the I, C to the J, such that I is less than J. Again, we will not write down the grammar for this, but you can do it as an exercise. You can write down a grammar to generate L22. Now, if once we complete these ones as well, it should be easy to see that we can combine them in a union. So basically generate a grammar S. S may correspond to strings generated with S11. Basically all strings of this format, A to the I, B to the J, C to the C to the star. Number of A's is greater than number of B's, and we have any number of C's. Or we can have strings of this format, number of A's is smaller than number of B's, and followed by any number of C's. So we can have S12. If you write down the grammar for these ones as well, S21 or S22. Now this grammar is capable of generating all such strings that we had defined earlier, A to the I, B to the J, C to the K, such that number of A's is not equal to number of B's, or number of B's is not equal to number of C's. Let's do yet another example, but in this one, let's try to do an example in the other direction. So far, we were given a language, we were trying to write down the grammar that generates it. Let's do the opposite now. So, given the following grammar G, context-free grammar G, defined as with the following rules. S is the starting variable. One rule is AS, another rule is SB, another rule is A, another rule is B. Given such a grammar, let's see if we can define the language that this grammar generates. Let's first try to do some sample derivations starting with S so that we can have an idea of the language corresponding to this grammar. I can start with S. Let's say I can expand this S with this rule. I will have AS. I can do another derivation and then expand this S with again the same rule with AS again. So this A corresponds to this A, and for this S I will have AS. Yet another one, I can do the same thing. Instead of this S, just write down AS, AS. Let's now use some other rule. I will have these 3 A's, already existing 3 A's, and for this S I will this time expand it with this rule, SB. If I do another derivation continuing with this one, let's say now we can, instead of this S, we can use A or B or any of these rules. For this case, let's just use B. A. Instead of S, we expand it with B. This is the already existing B. So such a string will be generated by this grammar. At home, you can try other derivations, other sample derivations, to see what types of strings you get from this grammar. So if you do enough number of exercises regarding these derivations, you will be able to see that the language that corresponds to this grammar is as follows. L, W in A, B plus, W consists of strings of A's and B's, but W should not be epsilon because we cannot have epsilon with such a grammar. So that's why we say plus, such that W does not contain the substring BA. Okay. If you do enough derivations, you should be able to see that with this grammar, it's not possible to have an A occurring after B. Okay. Although this gives us an informal idea, normally what we should do is prove such a claim. What is our claim in this case? If we are claiming that this language corresponds to this grammar, we need to prove the following: that any given string W belongs to this language L if and only if this W belongs to the language generated by this grammar L of G. And remember that for such claims, since we have an if and only if claim, we have two directions to prove. One of them is if W is inside the language generated by this grammar, if W belongs to L of G, then W also belongs to this language. And a second direction, if W belongs to this language L, then this means that W also belongs to the language generated by the grammar G. If we formally prove that both of these are true, then we can definitely say that this language corresponds to this grammar. Okay? For this time, let's try to prove each of these claims. Let's look at first the first part, the first direction. That is, if W is in the language of the grammar, then W belongs to the described language. Okay. We will again make use of proof by induction to do such proofs. Okay. So proof by induction based on length of our inductive proof will be based on the length of W. for our base case, basis, let's see the shortest possible strings that belong to our the language of our grammar. The shortest possible strings will be generated by these two rules, A or B. So W can be A, W can be B. Okay, if W is already A, it's easy to see that W belongs to the language description. That is, it doesn't contain substring BA. So W, if this is the case, W is in L. Same goes for W being B. It doesn't contain BA. This means that W belongs to the language L as well. This is for the base case. For the inductive part of our proof, let's assume that this claim is true for all shorter strings. Okay, so assume for all strings W prime such that length of W prime is less than certain length K, that this claim is true if W prime belongs to the language of our grammar, then W prime already belongs to the language as well. Let's assume that this is true. Now we will try to do the same thing. We will based on this inductive hypothesis, we will try to prove that for W with length exactly equal to K, if W is in the grammar, is in the language generated by the grammar, then W also belongs to the language. Okay, let's start with consider some W such that length of W is equal to K and such that W belongs to the language of our grammar G. Let's revisit our grammar G. Our grammar G was in this format. Now length of W is equal to K, and we are assuming that K is already greater than 1. Then this W, if it is generated by our grammar, it must be generated using one of these two rules. Okay, so for K greater than 1, there are two possibilities. Case 1, W generated by the rule S goes to AS. Okay. If W is generated by this rule, then we can see that we can apply our inductive hypothesis to the variable S in here, okay, such that this S can generate this W prime such that this W prime belonging to the language of the grammar, then W prime must belong to the language definition. Okay. Now, if W prime is in LG, then we know that W prime belongs to our language. So we basically have W being equal to a W prime such that W prime is in the language. Note that the definition of our language says that any string that doesn't contain the substring BA. Now, if W prime is in the language, W prime doesn't contain BA. If W prime doesn't contain the substring BA, then neither does W. If this is the case, W does not contain substring BA, and W belongs to the language. Okay. Now, this covers the first case if our string W is generated through this rule. I won't completely do the case 2 as well, but it can be done in a similar fashion. Case 2 covers the case where W generated by the second rule, generated by the second rule, which says S goes to S and B. So at home, as an exercise, write down similar arguments similar to the ones we have done in here, to prove that if W belongs to the language of the grammar, then W belongs to the language for this case as well. This covers case 2. Remember that to prove the one-to-one correspondence, our overall claim had 2 parts. Now we are done with this first part. In the second part, we need to prove that if the string belongs to the language, then it can be generated by the given grammar as well. Any string in here can be generated by this grammar. To prove this part, so the second part, if string belongs to the language, then the string can be generated by the given grammar. Again, let's consider several cases. So remember the definition of our language, L. It should be the strings AB plus such that the string doesn't contain the substring BA. Okay. So what are the cases? W can be equal to simply A. W can be simply equal to B. If W is A, it's easy to see that W can be generated by our grammar G using this rule. Similarly, if W is equal to B, then it should be easy to see that W can be generated by our grammar G by this rule. Okay, so in both cases, W is in the language generated by the grammar. Okay, this covers the case where W has length 1. So length of W is equal to 1. If length of W is equal to 1, this claim is true. Now consider the case where length of W is greater than 1. Now, if length of W is greater than 1, we will consider 2 subcases. One of them is W starts with an A, followed by some string W prime. The second case is W may start with a B, and followed by some W prime. Now if we check the first case, for the first case, W starts with A followed by some string W prime. If W belongs to the language, then what is the property that we expect from this W prime? It should be the case that W prime should also not include any substring BA, because W doesn't contain any substring BA. So W prime does not contain any substring BA. Now if W prime doesn't contain any substring BA, this means W prime is inside our language. And remember that using induction, we can assume that this statement is true for all shorter strings W prime. So for our W prime with smaller length than W itself, we can assume this statement is true. That is, if W prime belongs to the language, it can be generated by G. So by inductive hypothesis, W prime can be generated by our grammar G. Now if W prime is, if our grammar G is capable of generating this W prime, then W actually corresponds to a string generated by our grammar as well, because we have the following rule that says if you can generate some W prime through this grammar, through our starting variable S, then you can add an A and get another string generated by our grammar G. And that is exactly what W is. W prime is generated by our grammar G by derivations from S. This means that this string, this new string W, is also generated by our grammar G. So this is true. For the second case, if the string W starts with a B, if the string W starts with a B followed by some string W prime, what can we claim about W prime? in this case, we can even claim something stronger for W prime. We can say that W prime does not contain any A's, any symbol A. Because if W prime contains a symbol A, you will see the occurrence of the substring BA in the string W, which shouldn't happen because we want string W to belong to the language L. Okay. Now, if W prime does not contain any symbol A, then this means that W prime is in the following format. W prime is equal to B plus. W prime consists of B's, basically consists of positive number of B's. If W prime is in this format, W prime consists of a positive number of B's, at least one B, then it's easy to see that W prime can be generated by our grammar G. So take a look at our original grammar. It should be easy to see that with this grammar, we can generate strings that consist of any number of B's. 1B is also already possible. For 2B's, I can use this rule, SB, and then extend this S with a B, and I will have 2B's. For 3B's, again, I can do 3 derivations of this rule. For 4B's, I can do 4 derivations of this rule, and so on. So this implies that this W prime can be generated by our grammar G. If W prime can be generated by the given grammar, and W is in the format B and some string generated by the grammar, let's again take a look at our grammar rules, then we can see that this W, we will be able to generate it through this rule, SB. Okay. If this is the case, then W is also generated by L of G, because W prime is generated through this rule SB, and W itself will be derived from W prime using yet another derivation of this rule SB.